right? And this is the critical value we have. So anyone tell me we based on this result, so I will reject or fail to reject the null hypothesis. I will reject or fail to reject the null hypothesis. Based on the results, I will reject or fail to reject the null hypothesis.
You will reject it.
Yeah, because here you can see the z statistics here. It is larger than the critical value, right? So we have the z larger than the critical value, right? Critical value. So this would lead to we will reject the null hypothesis, right? We reject the null hypothesis, right? Reject the null hypothesis. That means the null hypothesis say no significant impact, right? So if we reject it, that means the impact of education on wage here, right, is statistical significant. Yeah, significant. At well, okay, here we define at the 5% significant level, right? 5% significant level. So this is the way we can look at. We check whether one coefficient is significant or not, right? And you can see here we have coefficient, we have standard errors, and we calculate the z here. This is our z value, right? And here, actually in the result, they also offer us the t here or the z here. Yeah, because here the number of observation, right? The they use the student distribution t, but the number of observation is very large, right? This would lead to the result for the student distribution. It is similar to the result for the normal distribution. And here you can see we have the same z statistics, right? And uh, actually, if you use the table, the student distribution table to locate the critical value, you get the same critical value here. Yeah, and in this situation, you can see they divide the DF here. DF here equal to 524, right? So we know that the DF here equal to n minus k minus 1, right? And the number of observation here, the 526, right? Minus k. K, this is the number of independent variables, right? Independent variables. So we already have education. That means the k equal to 1, right? Minus 1. And you can see here, we have the degrees of freedom equal to 524. Yeah, 524, right? So because we can use the student distribution for both the sample size is smaller than 30 and the sample size larger than 30. So this will lead to the mega start. We'll use the student distribution here, right? Because when sample size increase, the student distribution is low to normal distribution, right? And so they use the student distribution here. Yeah, but the result for if the sample is very large, right? The size is similar for if you use the student distribution or normal distribution. Yeah. Uh, yeah, because we cannot use the normal distribution if the sample size is smaller than 30 and we do not know the population standard deviation, right? So it is for easy to make a start here, provide the result for the student distribution. Yeah, and but if sample size is large enough, we can use the normal too. Yeah. And you can see here, this is the way we test the hypothesis, right? We have the coefficient, we have the standard errors, and we have the t here. But remember here, the t here is to test whether the coefficient here equal to 0 or different from 0. Yeah. But if we would like to test whether the coefficient here equal to a given number, for example, equal to 1, equal to 2, right? You need to change the z statistics here. For example, if you would like to test whether the coefficient here equal to 1, that means here the number here is 1. And actually the values here it is not, you would like to test equal to 1, right? So the value here it is different from here. Yeah, different from here. So remember here, the t statistics here is to test whether the coefficient here equal to 0 or different from 0. Yeah, is 0. Equal to 0, different from 0. Yeah, and here. So any question here?
Can you do the mega start step again, the process to make this table again?
Okay, yeah, okay. So you asked me how to create a relation, run regression model, right? So we use data here. Yeah, we use data here. And then we use the mega start here. Mm. Yeah, mega start here. And in this mega start, right, you can say that we have the scatter loss we already know in the session 2. Correction is the session 3, right? And we have regression. Now we have regression here. And in the regression, we need to locate the independent variables and dependent variables, right? Independent variable and dependent variable. So out in our data sets, we have the, let me see, yeah, we have the independent variable. For example, I would like to estimate the impact of education on wage. That means the education is a dependent variable. I need to locate dependent variable here. Yeah, right. Yeah, yeah. And okay, I will close this file. Yeah, let me see. Mega start here. Mm, Regression. Okay, we need to locate the independent variable, right? It's the education. Yeah, here. Education. And we need to locate the uh, dependent variable, right? Dependent variable. For example, investigate impact of education on wage. That means wage here is the dependent variable here. Yeah, dependent variable, right? Dependent variable. And in our model, right, we also include the intercept or constant here. So we stick here, yeah, and we get a result. Yeah, so this result we have, right? Yeah. And so this is the way we test a hypothesis using the critical value, right? But different from the one sample test, right? We need to calculate the z statistics by ourselves, the standard errors by ourselves, right? But now the megastat provide us, right? So this way we use the critical value, right? But we know another way to test a hypothesis. That means we use the critical value, right? We can use the critical value, no, sorry, the B value. You remember, to test a hypothesis, we know that if B value here, right, B value here is smaller than a significant level. So we will reject the null hypothesis, right? And for the one sample test, we need to calculate the B value by ourselves, right? We need to calculate the B value by ourselves. But here in the megastart, they also offer us the B value here. Yeah, so this is the value B value we have, right? The B value. That means the B value here for the intercept or the constant. And here, this is the B value for the education. Yeah, education. And okay, actually here, this is a very small number, right? When you see the number like this, it's a very small number, right? It's very small number. That means we have it is equal to zero. Actually, it equal to zero. Yeah, it equal to zero. And you can see here, when we test a hypothesis, I think it's better if you use the B value here, right? Because here we just say the B value, right? The B value for the education, right? Is smaller than, for example, we choose significant level and 5%, right? This would lead to, we will reject the null hypothesis, right? We reject the null hypothesis. That means it's similar here. The impact of education on way is significant. Yeah, and this, okay, yeah, the impact of education is significant at 5% significant level. So I think for the relation, it's easier for you to use the B value to test the hypothesis, right? You just compare the B value and the significant level, and then we know that we will reject or fail to reject null hypothesis, right? If B value is smaller than significant level, we just say the impact of education on is statistically significant at 5%. Yeah, at 5%. Yeah, and it is easier for us, right? Because here we no need to calculate the reticle values, all right? We no need to remember the reticle value, but we just define the significant level alpha 1%, 5%, or 10%. Then we can test the hypothesis. Yeah. And so any question here?
I want
And
to ask a question.
yeah, yeah, okay.
I'm so sorry. For example, for the H1, it would be the beta education will different from one. So can we conclude that it equal to it equal to one?
You mean that if S1 here is different from
Yeah,
1? Yeah.
yeah,
And then we will reject or fail to reject. Okay.
yeah, yeah.
For example, now we will test whether the coefficient here equal to 1 or different from 1. Yeah, it's okay. Yeah. For example, now you would like to test whether, okay, no, sorry. Okay, now you would like to test whether the coefficient here is equal to 1 or different from 1, right? That is your question. And okay, we
Yes.
would like to test whether this coefficient equal to 1 or different from 1, right? So because here it is equal to 1, so we cannot say it is significant, not significant here because it's a given number, right? So we just say our hypothesis is equal to 1 or different from 1. And similar here, we define the significant level alpha here equal to 5%. And here is a two-side test, right? And 5% significant level. The critical value here to still 1.96, right? 1.96. And then we have the uh, z statistics here, right? The z statistics here. The z statistics is the sample coefficient, right? The sample coefficient. And the value we would like to test here, it is not 0, but it is 1. Yeah, we minus 1. Because here we would like to test whether the coefficient equal to 1 or different from 1, right? So we have the sample coefficient minus the value we would like to test here, right? And then we divide the standard error for the education. Yeah, and you can get the z here, right? So it is uh, the coefficient minus 1, right? Divide the standard errors, right? Here. So based on this result, we will reject or fail to reject the null hypothesis. Okay, anh Thư.
We will fail to reject
Why fail to reject? So it is two-side test.
because
We
it's
will reject
smaller
if
than.
for the two-side test here, right? We will reject if absolute value of z larger than z alpha over 2, right? Z alpha over 2. Here, we have the z and we have critical value here. So this will lead to so we have absolute value of z. Copy this one. Okay, absolute value of z here larger than, right? Critical value, right? Critical value. This will lead to we will reject or fail to
Reject.
reject. Because it is larger than, right? That means we will reject the null hypothesis. Why? When we reject the null hypothesis, that means we have sufficient, right? Sufficient evidence to say the coefficient Okay, the coefficient and education here, right? It's different from one. Yeah, different from one. Yeah, the me when you say significant here, that means we say it is the impact here. It is significant and different from zero. Yeah, actually the statistically significant here. That means it's different from zero. Yeah, yeah, significant here. Okay, sorry. Significant here equal to different from zero. Yeah, if you say the statistical significant, that means it is similar with the way you said the impact of education on waste. Is it different, right? Different from zero. Yeah. And in this situation, you would like to test whether the coefficient different from one. So this will lead to you say the impact of education on here is different from one. Yeah, or we have sufficient evidence to say the coefficient here is different from one. Yeah. So this is the
Yeah.
conclude. If we test the hypothesis equal to a given number, it is similar to section 8, right? Section 8. So it clear for you.
Yeah, it's really clear. Thank you.
Yeah. Okay, here, right? So we can use the radical value or we can use the b value, right? And the b value here. Yeah, the b value here. Uh okay. Yeah, and you can say here, we already know how to transfer the estimation result to the equation forms, right? To equation form, right? That means we have the embedded value of dependent variable, we have the constant, we have the coefficient, right? And we have the independent variable, right? And you already know the number, the sample size and the R square, right? The R square here, yeah. So in addition to the coefficient here, we also report the standard errors here. Yeah, the standard errors here. Yeah. So for example here, if they ask you to transfer this result to the equation form, right? The equation form. So we have the weight here, expected value of weight, right? Expected value of weight here equal to, right? So the intercept here we have, you have uh this is the intercept you have, right? The constant you have, right? And then we lost, right? The coefficient on the education 0.5447. And then we have the education. Yeah. So let me see. Okay. Education, right? So you can see we have the embedded value. Yeah. Yeah. So this is a model. We have embedded value weight, right? And we have the coefficient. We had intercept here, and then we have the coefficient on education. And you remember we also report the number of observation here. It is the number of observation 526, right? 526. And we also provide the R square here. R square in this situation equal to 16.5%. 16.5%. Yeah, right? Yeah. And in addition, we also report, right? We also report the standard errors here. Yeah. So the standard error for the constant. Yeah. The standard errors for the constant is this number, right? 0.6877. Yeah. And the standard error for the education. Yeah. The education. 0.0535. Yeah. So here, this is the way we report the estimation result, right? So we have the uh, coefficient, we have the intercept, we have the coefficient, and we also provide the standard errors here. Yeah. So and number of observation and R square. Yeah. For example here, yeah, we have the dependent variable, the constant, the coefficient, yeah, and the number of observation. And based on this result, you can test whether this is significant or not significant. Yeah. And for example here, right? So we have this equation model, right? we will test whether the coefficient of high school GPA is significant or not significant. Yeah, significant. That means it's different from zero. Yeah. And then you can see here, we have the statistics, right? You see the coefficient minus zero, right? And divide the standard errors. And then we have the t, right? And because the number of observation here is very large, right? And either we can use the student distribution or normal distribution, right? Although the critical value for the student distribution and the normal distribution is different a bit, but the decision whether you reject or fail to reject the null hypothesis, it is similar, right? Because here the t very large here, so the student distribution here and critical value here is small. The critical value for the student distribution and normal distribution is very small here. So we reject the null hypothesis, right? Reject the null hypothesis here. That means the effect of high school GPA is statistically significant, right? Significant. Or here we say the significant different from zero. Is similar, right? Here you can say it is statistical significant or the significant different from zero. Yeah, at 1% significant level. Yeah, at 1% significant level. And for the test hypothesis here, we say, right, in the regression coefficient, right? So the t in the t statistics in the megastat result, it is so to test whether the coefficient is different from zero, right? In the two-side test, is similar here. I already showed you, right? So the coefficient, the t here, is to test whether this coefficient is different from zero or equal to zero. Yeah, equal to zero or different from zero. Yeah, two-side test. Yeah, and if the degrees of freedom is large enough, right, is large enough, so we can the critical value for the student distribution equal to the critical value of for the normal distribution here. Yeah, normal distribution here. And you can say that here we have the critical values at 10% significant level. It is 1.645. Yeah. And here it is 5% significant level. It is 1.96 and 1% significant level. It is 1.576, right? But it is for two-side test, right? Two-side test, and when the degrees of freedom is large enough, right? That means it is larger than 151. Yeah, 51. And yeah, and similar here, we would like to test whether the coefficient equal to a given number. Right, I already showed you here. We would like to test whether the coefficient is equal to one or different from one. Yeah. So here we have we also calculate the t, right, and we make decision it is similar. Yeah. For example, here, yeah, we have the coefficient. It is similar with the way I showed you. Yeah. The t or larger than the critical value. So this will lead to we reject the null hypothesis. And the p-value here, right? The p-value here, it is yeah, we compare with the significant level, right? If p-value is smaller than 10%, that means we reject the null hypothesis at 10%. Yeah. And smaller than 5%, that means reject the null hypothesis at 5%. That means, so if we reject the null hypothesis, that means the impact of, right, S on Y is statistically significant at, for example, at 10%. In this situation, we would like to test whether is it the the coefficient equal to zero or different from zero, right? And you compare, right? You compare with the significant level, right? If you reject at 10%, that means the impact of S on Y is statistically significant at 10%. Yeah, significant level. Yeah, and it is similar for 5%. It is similar for 1%. Yeah. So any question here? So uh I introduce the I mean we have two session and no two lecture for the session relation because it is one important session after the midterm exam, right? Yeah. So uh, at least you need to know how to interact the coefficient, how to test how to test the significance of the coefficient. Yeah. So, and after we test the hypothesis, it's similar to the sampling distribution. Here we also calculate the confidence interval, right? So we have the sample mean, but we do not know the population mean, right? So we use the sample mean to draw conclusion for the, okay, let me see. Okay, here, we we do not know the population mean. Yeah, population mean. So we use the sample mean here, right? The sample mean here to calculate an interval for the population mean. Yeah. For example, we use the sample mean here, we minus the margins of error. We use the sample mean here, we lost the margins of error, right? Margin of error here. And we have the interval for the population mean. Yeah, population mean. And similar here, we do not know the population coefficient. Yeah, coefficient. We use the sample, right? The sample to estimate, and we get the sample coefficient here, and we minus the margins of error, or we lost the margins of error, and we can calculate the confidence interval for population coefficient. Yeah, population coefficient. Yeah, and the way we calculate this similar, right? This similar. Okay, here we have the coefficient, population coefficient, but we do not know, right? We do not know, right? So here we have the sample coefficient, right? We have sample coefficient. That means we use the sample. We estimate, we get the coefficient on beta j. Beta j here may be beta 1, beta 2, beta 3. Yeah. And here we have the margins of errors, right? The margins of errors here. And actually, the margins of error here, it is similar. Yeah. Okay, okay, it is Z alpha over 2. Yeah, Z alpha over 2 for 10% significant level, right? For 10% significant level, Z alpha over 2 here is 0.5. Yeah, because in some textbook they define the critical value here. It is C, right? The C and Z alpha over 2. Yeah, okay. And this is 90% confident interval, right? We have the sample coefficient. Yeah, sample coefficient here. And we minus the margins of error, right? And you remember that we have the margins of errors here. Margins of error, it is Z alpha over 2, right? Time with the standard errors. The standard errors here, it is the population standard error, and divide the square root of sample size, right? Sample size. But for the regression, they already calculate for us the standard errors here, right? The standard errors here. Yeah, the standard errors here. This will lead to, right? So we have the critical value Z alpha over 2 time with the standard errors of this coefficient. Yeah, and similar here, we lost the margins of error. It is Z and okay, sorry. Z alpha over 2. Yeah, and similar here, we have Z here, Z alpha over 2 here, 85%. That means we have the Z, yeah, we got 2, and this Z2. Yeah, so we have the similar, right? We have the 90% confident interval, 95% confident interval, and 99% confident interval. Yeah, 99% confident interval. And the critical value here, if you do the normal distribution, it is similar, right? For example, for the 10% significant level, the critical value here is 1.645. And 5% significant level is 1.96, and 1% significant level it is 2.576, right? And if it is for the normal distribution, and for the student distribution, right? For the student distribution, you need to define the critical value using the student distribution table, right? Student distribution table, and the degrees of freedom here, because we have many independent variables, right? So the degrees of freedom here, n minus k minus 1. Yeah. So, okay, see the result. In this result, you can say that they offer us the degrees of the confidence interval, right? They offer the confidence interval for the 95% confidence interval, right? And you know how to calculate this one. So we know that this is the lower bound, right? The lower bound, we have the coefficient, right? The coefficient here, and we minus the margins of errors. Margins of error equal to the critical value, right? The critical value times the standard error. And here, if we calculate the 95% confidence interval, that means the critical value equal to 1.96. Because here we have the number of observation is very large, right? 8,526. So this really to we use normal distribution here, right? And here we have the standard errors here. Yeah. And this is we get the result. Yeah. Yeah. Because here they use the student distribution, right? So it is, I mean, the result is different a bit, but it's very small different, right? So okay, we use this one. Okay, okay, yeah. So we have the coefficient, right? And we have the critical value, and then we have the standard errors. Yeah, easy lower bound. And similar for the upper bound, right? So we have the coefficient here, time the critical value, time the standard errors here. Yeah, standard errors here. Yeah, and you can get the result. Yeah, you can get the result here. And when you would like, it offer us the 95% confidence interval, right? But how about if we would like to calculate the 95%, 99% confidence interval? So we just change the critical value here, right? For example, for 99% confidence interval, this is normal distribution, right? We have 2.16 here. Yeah, and we have the 99% confidence interval. Yeah, 99% confidence interval. Yeah. So any question here? So any question here? Mm-mm. And after we have so we go to the last one. This is the multiple regression analysis with qualitative information, right? That's mean here. Okay, for example here, we have education, right? Education, it is a numerical variables, right? It is similar for us to estimate because, for example, numerical variables, the number of years 11, right? Similar here, the number of uh, years is experience, right? That's mean the number of years of experience. So it is numerical variable too. It is